I was hoping my house would warm up today, but I don't think it's working because I took off my beanie and then I put it right back on. You lose a lot of heat from your head when you're bald. Anyway, something to look forward to for some of you, maybe. Let's talk about graphical behavior of polynomials. This is a good one. I like this one. This whole 4.2 and 4.3 polynomials and rationals, kind of dry. We're just learning about how certain functions work. We're not using them that much. I think the using of the functions more exciting. We're just kind of learning the nuts and bolts, and we'll use the nuts and bolts later. So a turning point of a graph is where it turns. It's where it changes from increasing to decreasing or vice versa. So we know what these look like, right? So here are turning points. It's going from increasing to decreasing, and then it's going back to increasing. So where it switches from going up to down or vice versa, that's just a turning point. So we got a little property here. If a polynomial has some degree, any degree, let's call that degree n. Some number n, that's the degree. Then it has at most that many zeros. And it has at most that many turning points. So it could have fewer. Like this is an example of a fourth degree polynomial. It almost has a zero. Certainly doesn't have 4 zeros. It actually only has 1 turning point. But usually when we think of fourth degree polynomials, we think of something that looks like this. They're both fourth degree polynomials. The idea is it can't have more than 4 turning points if it's a fourth degree polynomial. It can't have more than 3 turning points, actually. 1, 2, 3. You can't make a fourth degree polynomial that has more turning points than this. So let's use those properties and previous sections to say, what do we know about the degree and leading coefficient of the polynomial below? Okay, let's just go in steps. Let's talk about long run behavior. Long run behavior says we know something about the degree and the leading coefficient. To the left, it's going up, and to the right, it's going up. If we just focus at long run behavior, we ignore everything outside of this circle. Long run behavior is just forget about the middle stuff. Let's look at the ends. All right, we're skipping to the back of the book. Well, if the looks like this, remember that looks kind of like a positive quadratic. The degree has to be even. The leading coefficient has to be positive. Otherwise, it wouldn't look like this. So, okay, what else do we know? How can we use this property? We know it's got to be an even degree, but it can't be a quadratic. It's got too many turning points. How many turning points does it have? 1. Is this a turning point? It's curving. A turning point is where it goes from increasing to decreasing or vice versa. To the left of that point, it's increasing, and to the right of that point, it's still increasing, so that's not a turning point. This is a turning point, and this is a turning point. So we have 3 turning points. So it has to be at least a degree 3 polynomial. And we already know the degree is even, so degree has to be at least 3 and even. So that means the degree has to be at least 4 now. All right. And what about zeros? How many zeros are there? There are 1 0 here, 1 0 here, and 1 0 here. There are 3 zeros. Okay, so again, 3 zeros. Oh. 3 zeros. So it has to be at least a third degree polynomial. 3 zeros. So at least degree 3. But again, we already know the degree's even. I'm just going to say degree at least 3 here. We'll put it all together later. All right, well, if the degree has to be at least 3 and it has to be even, We know it's going to have an even degree of at least 4. And a positive leading coefficient. And that's our answer here. That's everything we can say so far. In the next page, we'll actually be able to say more. We'll actually be able to say this is at least a 6th degree polynomial. But for now, we just know that it's at least 4. So it turns out that this is the equation. This is the equation for that. What degree is it? Well, there's an x here. There's going to be an x squared here and an x cubed here. 6 x's total multiplied together. This is a 6th degree polynomial, like I guessed. Yeah, I know. I'm showing off a little bit. I know a little bit about polynomials. Pretty soon, you're going to be able to do the same thing. You're going to be able to show off to all your friends, too. Okay, so this is what the function looks like. So notice how each horizontal intercept behaves differently. Right? This horizontal intercept, I need to change colors. Blue on blue is not doing it, Jason. Right? When we cross here, that's one kind of crossing. Notice that this crossing over here, this is also not good for people who are red-blue colorblind. Gosh, I'm terrible with colors. I'm sorry. How it crosses here is a little different. How it crosses, well, this one, it just bounces right off. So notice that this first case cuts straight through, like an arrow. The second place like cuddles up to it and then crosses. And the third one bounces off. Well, notice what's happening. That's the one on the left. That's the one on the right. That's the one in the middle. Is that coincidence? What's the difference between these two factors? This has an exponent of 1. This has an exponent of 2. And that has an exponent of 3. Turns out it's not a coincidence. Bet you never saw that one coming. It's not a coincidence. So if a factor is repeated p times, so right, this is repeated twice. It's x minus 2 squared. So x minus 2 times x minus 2. It happens twice. Because of the exponent. This is maybe not the best example, because 2 could mean different things. Right here, the factor happens 3 times. It's being cubed. There are 3 of these multiplied together. We call that multiplicity. And if the multiplicity is 1, it's like an arrow shooting through the axis. If the multiplicity is 2, it bounces right off. If the multiplicity is 3, it kind of curls right up to it and then crosses and then zooms away after a while. That's always going to be the case. Don't believe me? Well, you should. I'm a math professor. I never make any mistakes. So let's look at some things. Let's look at x minus 1, x plus 2. So both of these have multiplicity 1. Right? We go directly through. Go directly through. But let's give one of these multiplicity 2. Whoa! Look what happens to this 0 now. When x is equal to 1, what's happening now? It's bouncing off. What if we gave the other one the same multiplicity? Hey! Now they both bounce off. Multiplicity 2, an exponent of that factor, of exponent 2, means it bounces right off. Do you think we're going to see the curl right up to it and go away if we make one of these a 3? Whoa! Look at that. Look at that. It's just like what we said would happen. It gets real close and then touches it and then it goes away. Ah. All right. What about 4? What do you think is going to happen for a 4? Look at this one right here. Look at this guy right here. See what happens when we make the multiplicity 4? Is that what you expected? It's bouncing off flatly. What about multiplicity 5? Oh, it's curling up to it, extra flat. Multiplicity 6, bouncing off, really flat. Multiplicity 7, curling up, really flat. Okay, okay. It's just the same stuff. Just gets flatter. So if the multiplicity is 2, it bounces off. If we have higher evens, it's just flatter, but the same thing. That's true for odd multiplicities. Oh, this second one would be higher odds. Right. And really what's going on, if we really zoom in, this kind of looks like a line, a first degree polynomial. If we really zoom in, this kind of looks like a parabola, second degree polynomial. And if we really zoom in, this kind of looks like a cubic function, a third degree polynomial. And that's why higher degrees look the same, is because higher degree monomials, 1 degree polynomials, they look the same. So that's really what we got here. Let's do some examples. What do we know about the degree here? Well, a lot of things. We know a lot of things about the degree here. The degree has to be even because of the long run behavior. It's going in the same direction, down to the left and the right. To know it's even. We know a couple other things too. Oh, I should mention this, right? Is a good thing. The degree of a function is at least the sum of the multiplicities. Right? What that means is that if there's something with multiplicity 1, something with multiplicity 2, and something with multiplicity 3, the degree has to be at least 6. That can be useful. I don't think it's mandatory, but it's useful. All right, so we know the degree is even. We could look at the turning points. Oh, that's not a turning point. There's one turning point here, a turning point here. There's 3 turning points. So the degree must be at least 4. And we can refine that later, right? Because here we have a 0 of multiplicity maybe 3, some odd. Well, the multiplicity is at least 3. Here we have a 0 of multiplicity 2, right? It's bouncing off. And here we have a 0 of multiplicity 1. It's going straight through. So I'm thinking it's at least 3, but looking at these zeros, add these multiplicities together, I think the degree should be at least 6. Okay? Really at least 6. That's what we know about the degree. What about the long run behavior? It goes down in both directions. As x either goes to positive infinity or negative infinity. As we go all the way to the right or all the way to the left, the function does the same thing. It goes infinitely down. The function goes to negative infinity. What about the intercepts? What are the intercepts? This is negative 10. We're counting by 2s, right? 2, 4, 6, 8, negative 2, negative 4, negative 6, negative 8. So the zeros are at negative 5, 0, and 4. Horizontal intercepts are at negative 5, 0, and 4. And the vertical intercepts at 0. Turning points, we kind of covered that. There's only 2 turning points. Oh, no, there's 3 turning points, right? It changes directions from increasing to decreasing here, and here, and here. So there's 3 turning points at those places, which is like, it's kind of hard to estimate. This is like -2, comma, we're counting by 20s here. Like -2, I don't know, 13, I don't know. Zero, 0, and then like 390. And we already said the multiplicities, right? So let's just answer that up here. This had multiplicity 3 because it's curling up and then going through. Maybe it's multiplicity 5, maybe it's multiplicity 7. Looks something like 2 or 3. Here, notice we're bouncing off the x-axis. We're bouncing off the horizontal axis. So it's an even multiplicity, probably 2. And this last one, it cuts right through. Multiplicity 1 for sure. You could answer that in a sentence, but I would honestly just take this too. With all this in mind, do you think this could be that? Oh my gosh. With all this in mind, could it be this function? Now let's look at it. We know the degree is even and at least 6. Is the degree of this even and at least 6? There's an x cubed in this term, an x here, so we're up to x to the 4th. Multiplied by another x. Okay, we got an x to the 6th. X to the 6th is plausible. A 6th degree polynomial is plausible. So the degree checks out. Long run behavior would be going down in both directions. Oh. Look at our leading coefficient. It's kind of hard to see the leading coefficient. We don't have this all expanded out. But the leading coefficient is what all the x terms are going to have, the biggest x terms. So we're going to have a 1x cubed that comes from this thing. A 1x from this, we have a 1x to the 4th, multiplied by a 1/50th x squared. We have a positive leading coefficient. Positive leading coefficient says it should be going up to the right. It can't be the equation. Got the wrong leading coefficient. This should be negative. This can't be the equation. So let's check the other things. Do the other things check out? Intercepts, does it have the right intercepts? An input of -5? Yeah, an input of -5 makes the whole thing 0. An input of 0? Yep, makes the whole thing 0. An input of 4? Yep, makes the whole thing 0. Good. And yeah, when the input's 0, the output's also 0. So yeah, it checks out, it has the right intercepts. Turning points? We can't really do that yet. That's calculus. We can check D once we get into calculus. E, multiplicities. Does -5 have a multiplicity 3? Yeah, it does. Look at that right there. Does 0 have a multiplicity 2? Yep. Look at there. X squared. X minus 0 squared. Does the 0 of 4 have multiplicity 1? Yep. There's a hidden 1 right here. That has the right multiplicity. So actually, it almost has everything right that we can check right now. But our answer is no. Because we need a negative leading coefficient. We have a positive leading coefficient. And if you graph this, it'll look pretty similar, but just flipped kind of. That's kind of what we're doing for graphs. It's maybe the harder section, but the most fun for me. You're probably going to see a question like this. Maybe not like this exactly, but this sort of question on a quiz or exam, because I love these ones. So let me know if any of this doesn't make sense, and I'd love to talk about it some more. Have a good one. Bye-bye.